Welcome all. This is a video presentation on the second half of the second module of the subject CS463 Digital Image Processing, which is offered as an elective to the 7th semester Computer Science and Engineering students under KTU. Myself Harikrishnan M, Assistant Professor in the Department of Computer Science and Engineering at Rajagiri School of Engineering and Technology. This is the syllabus for the second module. We've already discussed the first half of it in a previous presentation. We'll be discussing discrete cosine transforms, Walsh transform and Hadamard transform in this particular presentation. Discrete cosine transform is defined as shown in the equation here. C of Kn is what is used to represent the discrete cosine transform of an image. It has a value of 1 by root n if the value of k is 0 and the value of n lies between 0 and n minus 1. It has a value of root of 2 by n cos pi of 2n plus 1 into k by 2n. If the value of k lies between 1 and n minus 1 and the value of n lies between 0 and n minus 1. The one-dimensional DCT of a sequence u of n is given by v of k, which is calculated with the help of a parameter alpha of k, where the value of alpha of 0 is equivalent to root of 1 by n and the value of alpha of k is equivalent to root of 2 by n. The inverse transformation, that is u of n, is calculated again using the equation given here. Summation over k from 0 to n minus 1 alpha of k into v of k into cos of pi into 2n plus 1 into k by 2n. The image shown here represents the effect of DCT on a particular image. As you can see here, the first block of a DCT image contains the maximum value or the highest value of all, which is represented here as the white pixel or the white area in the top left corner. It is known as the DC coefficient. The remaining coefficients contain lesser values, most of which are 0. And this is an example for a DCT operation performed on an original image. Now, what are the different properties of DCT? Discrete cosine transforms are real and orthogonal. That is, C is equal to C star, which implies that C inverse is the same as C transpose. Cosine transform is not the real part of unitary DFT. However, the cosine transform of a sequence is related to the DFT of its symmetric extension. It is a fast transform, which means that there are algorithms present for fast implementation of DCT. Cosine transform of a vector of n elements can be calculated in big of n log n to the base 2 operations via an n-point FFT. It has excellent energy compaction for highly correlated data. Now the next transform that you have to learn is Walsh transform. Suppose the value of n is 2 raised to n, then the Walsh transform kernel function is represented as g of xu, which is represented using the given equation 1 by n pi of I equal to 0 to n minus 1 minus 1 raised to bi of x into bn minus 1 minus I of u. And the discrete Walsh transform of a function f of x denoted by w of u is given here. Here bk of z is the kth bit in the binary representation of z. The inverse kernel and the transform for Walsh transformation is shown here. Hadamard transform, which is also known as Walsh-Hadamard transform, makes use of Walsh function to calculate the transformation matrix. Unlike the previously discussed transforms, the basis vectors for Hadamard transform takes only binary values, that is either plus 1 or minus 1. The Hadamard transform matrices Hn are n by n matrices and can be generated easily using the core matrix H1 given here. So H1, which is the core matrix for Hadamard, is represented as 1 by root 2 into 1 1 1 minus 1, and the Kronecker product recursion can be used to calculate the higher values of H. So H2 is calculated as H1 cross H1. Hn in general is calculated as the Kronecker product of Hn minus 1 and H1. So therefore you calculate it as 1 by root 2 into Hn minus 1 being the first row and Hn minus 1 and minus Hn minus 1 being the second row. The examples for H0, H1, H2 are shown in the next slide. The Hadamard transform for an n by 1 vector is written as V is equal to Hu, where H is the Hadamard matrix, V is the transformed vector and U is the original sequence. And the inverse is given by U is equal to HV. As an example, for n equal to 3, the Hadamard matrix becomes H3 is H1 cross H2. and H2 is H1 cross H1. So H3 is basically 1 by root of 2 raised to 3, which is 1 by root of 8 into H2 matrices placed in the first, second positions of the first row, the first position of the second row, and the inverse or the negative of H2 placed as the second column, second row element. These are how the different basis matrices for Hadamard transformation is calculated. H0 is nothing but plus 1. H1 is 1 by root 2 into 1, 1, 1 minus 1, where the last entry is sign inverted. Similarly for H2, you place H1 in the 4 different positions of the matrix and then inverse the sign of the last H1 matrix. And H3 is calculated by placing H2 likewise. The general equation for calculating Hn of ij is 1 by 2 raised to n by 2 into minus 1 raised to I into j. The basis vectors for Hadamard transform can also be obtained by sampling a class of functions called the Walsh function. Hence, Hadamard transform is also known as the Walsh-Hadamard transform. The number of zero crossings of a Walsh function or the number of transitions in a basis vector of the Hadamard transform is called its sequency. The existing sequency order of these vectors is called the Hadamard order. These are examples of Hadamard transforms of monochrome images and binary images. A more clearer picture will be available in the textbook by Anil K. Jain. Now, what are the different properties of Hadamard transform? It is real, symmetric and orthogonal. It is a fast transform. The one-dimensional transformation of V equal to HU can be done in big O of n log n time. That is, number of additions and subtractions needed to perform the Hadamard transformation is big O of n log n to the base 2. The natural order of Hadamard transform coefficients turn out to be equal to the bit reverse gray code representation of its sequency S. The Hadamard transform has very good energy compaction for highly correlated images. Now, this is a table that shows the natural ordering against the sequency ordering of Hadamard transform coefficients for the value of n as 8. Suppose the natural order H is represented as value 0 to 7. Its binary representation is given as a 3-bit binary value. Gray code of S or the reverse binary representation is calculated by inverting the bits of the binary representation. So 000 remains intact, 001 becomes 100, 010 remains intact, 011 becomes 110, etc. The sequency binary representation B3, B2, B1 is calculated using the gray code of S, and the sequency S is generated according to the binary representation. So that's all about all the portions to be learned in the second module. There are problems to be calculated and practiced, which is not necessarily possible through a video presentation. So the references for learning the second module on image transforms are the textbook on image processing by A.K. Jain, and the URL shown here is an excellent reference that can be used to learn this particular topic as well. So thank you all for your patient hearing. I'll meet you with the next presentation at a later time.